Hello students, this video lecture will cover section 9.6, Composition of Reflections. Our learning goal for this lesson is to be able to find compositions of reflections, including glide reflections, and to classify isometries. So first we should note that any isometry can be expressed as a composition of reflections, which leads us to Theorem 9.1, our first theorem of chapter 9, which states that a translation or rotation is a composition of two reflections. Theorem 9.2 shows us that a composition of reflections across two parallel lines is a translation, and a composition of reflections across two intersecting lines is a rotation. So let's take a look at composing reflections across parallel lines. So we're trying to determine the direction and distance of the resulting translation. So the first thing that we want to do is we want to reflect R across line L. So if we take a look, by reflecting this capital R across line L, we end up with a figure that looks similar to this. So if we remember, this line, the line of reflection, and the point at which the line is reflected, every point P prime on this R is going to be the same distance from P to A as from A to P prime. So we can say that the total distance from P to P prime is 2 times the distance from A to P prime. The second thing that we're going to do is we're going to take this R and then we're going to reflect it again, except for this time we're going to reflect it across line M. And so here P prime is being reflected to P double prime. And again, this has to be a 90-degree angle based on our rules for reflections. And every point on this final R is going to be the same distance from P prime to B as it is from B to P double prime. So here we're going to say that this distance is going to be twice the distance from P prime to B. So first let's deal with the distance of the resulting translation. We go twice the distance from A to P prime, and we're going to add to that twice the distance from P prime to B. So these both have a 2, so let's factor the 2 out. So we have 2 times the distance from A to P prime plus from P prime to B. If we remember all the way back to chapter 1, we can use segment addition postulate here since these points are all 3 of these points, A, P prime, and B are collinear. We can take the P prime out and we can say that this is twice the distance from A to B. So the distance when we're composing reflections across parallel lines is twice the distance between the two lines. And so let's deal with the direction here. The direction is going to be the perpendicular to the first or second line. So it's going to travel perpendicular to the lines themselves. Problem 2 asks us to compose reflections, but this time dealing with intersecting lines rather than parallel lines. So we have 2 lines, L and M, that intersect at point C and form an acute angle that measures 70 degrees. We're trying to determine the image of R, first reflected across line L and then across line M. We're trying to determine what are the center of the rotation and the angle of rotation of the resulting rotation. So the first thing that we're going to do is we're going to reflect this R across line L. So here again, using our rules for reflections, we're going to get P prime, which is a reflection of point P. This is going to be a 90-degree angle, and these 2 line segments are going to be of equal length. That's based on our rules for reflections. And so then finally we're going to reflect the resulting image across line M. So here, every point P prime in the second R is going to have a partner, P double prime, in the third R. Based on our rules for reflections, we know that these two are going to be exactly the same length, and that this is going to be a perpendicular line to line M. So I've gone ahead and got out my compass, and I'm pretty sure that the center of this rotation is going to be at C. The reason for that is it seems to be the most logical point. So let's go ahead and open our compass so that we have one of these points. Now let's go ahead and draw an arc, and let's see, and in fact you can see based on this arc that in fact all of these points are touched by this arc centered at C. So the center of this rotation across intersecting lines is going to be the point of intersection. Now determining the angle of rotation is a little bit more difficult, but since we've actually already completed chapter 12, we actually have a slight advantage here. We have a chord, this red chord, that is cut perpendicularly into two equal parts by this line. So that's one of the things that helps us know that C is the center of the circle. In addition to that, based on what we know that these two pieces of arc cut, since the chord is cut into two congruent parts, these pieces of arc must also be cut into two congruent parts. And the same thing actually holds true for the arcs over here with the blue chord. So that tells us that this 70-degree angle is a central angle to the circle. And so one part of red and a part of blue gives us this 70-degree angle. So kind of in simple notation, if I take the one part of red that I've marked and add to it the one part of blue, so if we take the two parts red, one part blue, and add them together, we get 70 degrees. Well, the total angle that this has been rotated is two parts of red and two parts of blue. So we have two of these, so the angle of rotation is 140 degrees in this case. Let's go ahead and get rid of our compass here. We have 140, and we can see that the 140 and 70 are definitely related. So the angle of rotation, whenever we do this, the angle of rotation is going to be 2 times the angle created by the intersecting lines. So the center of rotation is going to be the point of intersection, and the angle of rotation is going to be twice the intersection of the two lines. So this leads us to the fundamental theorem of isometries. So in a plane, any two congruent figures with the same orientation are related by either a translation or a rotation, and therefore by two reflections. And if we suppose that two congruent plane figures A and B have opposite orientations, then first we reflect A so that we get A prime that has the same orientation as B. Thus, B is a translation or rotation image of A prime. And by theorem 9.1, two reflections map A prime to B. So the net result is that 3 reflections map A to B. So the fundamental theorem of isometry states that in a plane, one of two congruent figures can be mapped onto the other by a composition of at most 3 reflections. So if we have two figures that are congruent and have opposite orientations but are not simply reflections of each other, then there are a translation and a reflection that will map one onto the other. So a glide reflection is the combination of a translation and a reflection across a line parallel to the direction of translation. So here we can map the left paw print onto the right paw print. So first we move it forward, and then we flip it over. So in this case, to move one paw print to the other, we have to move it forward and then flip it. and we call that a glide reflection. So finding a glide reflection image. What is the image of triangle TEX for a glide reflection where the translation is x comma y goes to x comma y minus 5, and the line of reflection is x equals 0, which is the y-axis. Our first step is to draw the pre-image, which in this case has been done for us. Our second step is to use the translation rule. So in this case, our translation rule says keep the horizontal distance the same, but reduce the vertical distance by 5 in each case. So I'm going to take t and I'm going to move it down 1, 2, 3, 4, 5. So this is going to give me t prime. I'm going to take e and I'm going to move e down 5, which is going to give me e prime. I'm going to take x and I'm going to move x down 5, which is going to give me x prime. And so connecting these points, I can find the triangle after using the translation rule. Our final step is going to be to reflect across the line of reflection. So e prime is 1 square from the y-axis, so I'm going to go 1 past the y-axis, and that's going to give me e double prime. T prime is 1, 2, 3, 4, 5 from the y-axis, so I'm going to go 1, 2, 3, 4, 5 past. That's going to give me t double prime. And x prime is 2, so I'm going to go 2 past, and that's going to give me the final location that I'm looking for, x double prime. And finally, connecting these spots will give me the triangle glide reflected. So you can see it's been slid down and then flipped over. So then problem 4 asks us to classify isometries. So each figure below, there's 2, is an isometry image of the figure at the right. What type of isometry maps the pre-image to the image? So in this first case, the orientations are actually opposite. If you look at this, the letters are non-readable because they've been flipped around. So this image is not a simple reflection of the pre-image. So the isometry that leads to an opposite orientation, but is not a simple reflection, is a glide reflection. And in this second case, the orientations are the same. So the image is not a translation of the pre-image. The isometry that leads to the same orientation, but is not a translation, is a rotation. So sometimes we're simply turning the figure, other times we're both turning the figure and flipping it. And that concludes this video lecture, section 9.6, Composition of Reflections. Hopefully you understand that a composition of reflections leads to either a slide or a rotation. And there's an additional new type of reflection which is called a glide reflection. So this is the combination of both. Thanks for your attention, and I'll see you all soon.